Hey everybody, hope you're having a good day. Welcome back to the first official day of classes. And today we're going to be talking about reactions of acids and esters. Now, they have roughly the same reactivity. And if you go back and look at the acid derivative chart, which we've done a couple times, and I keep referring you to it, hopefully you'll get a clue that that's important, the acid can be turned into any of the derivatives in one step. The acid chloride, the anhydride, which we've already covered. You can also use it to form an ester, an amide, and finally the salt. Now, the other thing I want you to notice here about this chart is energy, let me put it this way. Reactivity goes up as you go up that chart. It keeps building, meaning the acid chloride is the most reactive and the salt would be the least. The thing I really want you to notice here, though, is that the ester and the acid are at about the same energy level. So in terms of the overall reactivity and predicting which way these are going to go, you're going to find the acid and the ester to be about the same point. Now, another thing that happens here that we haven't been able to see before, or had to see before, is the fact that with this, the acid and the ester, we get to the point where we are going to have to need to use the electrophilic and maybe on rare occasions, the nucleophilic pathway. It's very rare though. Part of the reason it's rare in the nucleophilic pathway is both the hydroxide. If you were trying to do a straight substitution here, you'd replace the OH with your nucleophile and you get hydroxide. And the same principle here on the ester. And you get there. Both the alkoxide and the hydroxide are poor leaving groups, mostly because they're so high in energy and they're quite reactive. All right, here's another reason, especially with the acid, that you don't want to use a nucleophilic pathway. Because you introduce a strong nucleophile, let's say this alkoxide, you introduce a strong nucleophile to the acid, instead of doing a nucleophilic attack, it's going to snag that proton off the acid first. Now, why is that? Remember, acid-base reactions are always faster than nucleophile electrophile. So the product you would actually see out of this is the carboxylate salt and the alcohol. Okay, so there's one reason we can't do that. If you're reacting an ester with a strong base, you have a couple more options. Now, some of the mechanisms that we're going to cover in this part are a little lengthy. So I may end up breaking this up into two videos, and then I'll label it part 1 and part 2, just so everyone can kind of keep up with what they're doing. So all that being said, let's look at how we turn an acid into an ester. But before I do that, I just realized this is a pretty good teachable moment. You've made esters before, through kind of a non-standard way, I might add, but it works. Remember the banana oil experiment? Where you took an acetate and an alkyl bromide and you did the SN2 reaction in the presence of DMF? And you got this. Whoops, wrong structure. And you got this as your product. Oh, my goodness, people, the tech gremlins are upon me today. That's not exactly it. Let's just pretend it is because I'm tired of fighting with this right now. This is how you made an ester before. So other reactions that will ship the acid over to the ester. The big one that everybody knows about is called the Fischer esterification. And if you're wondering, okay, this is named after a guy named Fischer, and you're wondering, I've heard Fischer before. Where have I heard that? Oh, where have I heard that before? Oh, where can it be? And the answer to that is, do you remember Fischer projections from discussing chirality, where your structure would look like this, but what you'd have is the bow tie approach for every one of those carbons? Same guy, M.O. Fischer, great German scientist, total jerkhead, but a great scientist. So, the Fischer esterification reaction looks like this. You take a carboxylic acid, you react it with an alcohol. What you get is, sorry, tech gremlins, this ester plus water. Now, before we go into the mechanism here, what acid source are we talking about? Here we're talking about sulfuric acid. It's the one that everybody uses principally because, unlike the other mineral acids, it provides a non-nucleophilic counter base for you to work with. All right, so let's look at the mechanism here. Actually, let's not yet. One more thing I want to say. It's a series of proton transfers and leaving groups. All right, let's see how this works. You start with your carboxylic acid. The lone pair of electrons on the carbonyl oxygen are going to deprotonate the hydronium. Equilibrium step, because remember, proton transfers on and off of oxygen are fast and reversible, which puts you here. And remember, what do we call it when we protonate the carbonyl oxygen to get the reaction to work faster? We call that priming the pump. Now in comes your friend and mine, the alcohol, which is going to nucleophilically attack that carbon and open up the carbon-oxygen pi bond, which now gives you this as your next intermediate. All right. So now we know what we can do here. Because this oxygen is positively charged, we can do a intramolecular proton transfer where the proton will be, well, protons don't actually move, they are moved, where the proton will be moved over to that OH group. Either one of them is fine. I just find this one much easier to write in. In another equilibrium step to here. And what do we know about OH2? It's water, it's tasty, and it's a heck of a nice leaving group. So now you're here. And we are almost home because the hydronium, water. Now, where did you generate water earlier here? Well, water was a leaving group right there, and you had a water up here that gave up its proton initially. So there's plenty of water around here for you to work with. Water pulls off the proton, and you get an equilibrium structure of this. Sorry I had to write that down there in that small corner, but it's the space I had. You get the ester and hydronium. Now, I'm almost out of time, so I want to cut this one off here. But what I want you to notice here is there's acid in the beginning and acid out at the end. So this is another one of these acid catalyzed processes, meaning you don't have to dump in 3 equivalents of acid to get this to work. 1 or 2 mils will usually do the job just fine. All right, this is the Fischer esterification, and I want to leave you to work on this problem. In essence, this is busy work, and I normally don't enjoy busy work, but this is a complicated enough mechanism that I think it's worth you looking at. I want you to do the mechanism for this. All right? Do that mechanism, see, and again, we know what the product is going to be, but I want you to get practice doing it. Final thing I'm going to say about this, let's flip back a page or 2. Let's look at this overall reaction here. In the start, you've got an acid and an alcohol, and in the product, you have an ester. You got to have some way of separating those because remember, this entire process is in equilibrium. And the way you can separate these is the ester is going to have a lower boiling point than either the alcohol or the acid because there's no ability to form hydrogen bonds. A distillation will take care of it for you. All right, folks, that's all for this video. Tune in next time when we talk about trans esterification. Have a good day. Talk to you soon.